はい、それでは本日最後のご講演となりました。最後の講演はドローンの暗号解析、スパイするドローンの検出についてベン・ナシさんからお話をいただきます。ベン・ナシさんはネゲブ・ベン・グリオン大学の博士課程の学生さんで元 Google 社員でいらっしゃいます。研究対象は幅広く多くの有名カンファレンスでの講演経験もお持ちです。今回は彼の2本の講演が採択され、本日と明日それぞれご講演をいただく予定です。ベンさんからは今回のテーマについて動画をいただいております。動画が終わりましたら皆様のご質問を、ベンさんご本人にお聞きしていきたいと思います。Our next session is drones cryptanalysis, detecting spying drones. Please welcome our speakers, Ben Nasi.
Okay, so hello Code Blue, and welcome to my talk about drone script analysis, detecting spying drones. Let me start by introducing myself. My name is Ben. I'm a computer scientist and a former Google employee. I'm a PhD student at Ben-Gurion University of the Negev and a researcher at Cyber at BGU. My research focus are security and privacy of IoT devices, and you can read more about my research at my website. This is a joint work co-authored by me, Raz Ben Netanel, Professor Adi Shamir, and Professor Yuval Alovich. It's a collaboration between Ben-Gurion University of the Negev and the Weizmann Institute of Science. Okay, so let's review the agenda for today. We will start by discussing the motivation for the research. We will then continue by discussing the detection scheme and the Wi-Fi FPV channel. We will then review and understand the 3 stages of detection that involve in detecting a spying drone. We will discuss about how this entire method can be applied invisibly, and at the end, we will conclude this talk. Okay, so let's start with the motivation, and let's start with the good news. You are about to get your pizza delivery much more faster, and as a result, much more warmer. And this is the result of using drones for deliveries. And this is the good side of drones. They have great potential, and deliveries is only one of them. However, this is how the ugly side of drones looks like. Drones are turning to a great threat to individuals' privacy in recent years. Many people use drones to spy after their neighbors, to spy after their spouses, to spy after random people, and to spy after celebrities. And as I mentioned, drones are actually turning to a great threat to individuals' privacy, a new threat that we haven't seen before. Okay, 2 things also need to take into consideration. The first thing is that the drone adoption rates are actually increasing around the world. And this is the result of businesses. Many businesses have started to adopt drones for various purposes. And also, the second thing that needs to be taken into account is that regulations are being changed for allowing drones to fly in populated areas. Basically, many areas around the world started to adopt an open skies policies in neighborhoods and in cities. So the conclusions are that many drones are about to fly in populated areas in the near future. And also, as a result, the amount of spying drones incidents is expected to increase significantly. Okay, so this is the research question that we try to answer in this research. In an open skies era in which drones can fly between us, how can we determine whether a drone that is passing near a house is being used by its operator for a legitimate purpose or an illegitimate purpose? And if you will look on the feature to the right, you will see that a drone is boxed in yellow, is being used from the same location to spy after an organization. And this is what we call an illegitimate use. And for a legitimate use of taking a selfie. Okay, so we actually went to the literature in order to find what methods are being used for detecting the presence of a nearby drone. And we found that there are many methods that are very effective at detecting the presence of nearby drones. And some of them are radars, others are video cameras, others are LiDARs, and other methods include microphone arrays. Sometimes these methods are even combined together to achieve a highest level of detection of drones. And basically, as you can able to understand, these methods able to detect the presence of nearby drones very effectively. However, we also claim that methods for detecting the presence of a drone in an open skies are, in our opinion, irrelevant because the presence of drones is no longer restricted in populated areas, and this is the result of the things that I mentioned before, regulations that are being changed around the world. And as you can see, the difference between a legitimate use of a drone and an illegitimate use of a drone depends on the drone's camera orientation rather than on the drone's location. You can see again in the picture to the right that an illegitimate use and a legitimate use of the drone are, in this case, depends on the drone's orientation because in both the camera orientation because in both cases they were the pictures were taken from the same location. So the conclusion, an important conclusion, is that the geofencing methods are irrelevant for detecting a spying drone in an open sky cell. Okay, so let's review the objective of this talk. The main objective is to detect a spying drone using cryptanalysis. And we'll start by trying to classify suspicious radio transmission as a first-person view channel. We will then discuss about how the first-person view channel can be, how can we detect whether the first-person view channel is being used to spy after the victim. We'll continue by discussing on how to locate the spying drone in space. And finally, we will discuss about how to detect a spying drone without revealing it to the drone's operator. Okay, so let's review the detection scheme, and the detection scheme is as follows. We assume that there is some malicious drone operator that is using a Wi-Fi FPV drone to spy after a victim that can be located up to 5 kilometers from the malicious drone operator. And there is some kind of spying detection mechanism that is used to detect spying drones. And the spying detection mechanism is connected to an RF scanner with a proper antenna for intercepting a suspicious radio transmission. Now let's talk about first-person view channel. First-person view channel are communication channels which designed to two things. The first thing is to stream the video captured by the drone to the operator's controller. And the second thing is to maneuver the drone. And there's the downlink and the uplink. And in this research, we focus on the downlink of the FPV channel that is used for video streaming. Now, Wi-Fi FPV channels are the most commonly used type of first-person view channel because for drones, because it eliminates the need to develop a dedicated controller. And as a result, any kind of device that with an integrated Wi-Fi network interface card can be used as a controller. This can be your smartphone, this can be your tablet, this can be your laptop. Moreover, Wi-Fi FPV channel now allow an operator to fly its drone to a distance of up to 5 kilometers. And as you can see, many new drones using this technology of Wi-Fi FPV channel. DJI use it in 3 of its models, which are the Mavic Air, the Spark, and the Mavic Pro. Okay, so when you are using Wi-Fi as communication channel, you actually get the encryption and the modulation for free just by using the standards of Wi-Fi. It means that when Wi-Fi is used for FPV channel, the video stream is encrypted. However, does it really make the video stream confidential? And during the next 20 minutes, I will try to convince you that the answer to this question is no. Okay, so let's talk about how we intercept a first-person view channel. So given a suspicious Wi-Fi transmission, we create an intercepted bitrate signal, which consists of two stages. The first stage is to sniff Wi-Fi packets. You can do it easily by enable network interface monitoring mode. Sometimes it calls attack mode. And sniff Wi-Fi packets using a sniffer like Airmon that allows you to sniff nearby Wi-Fi packets. Now, the payload of the packets is encrypted. However, we actually extract data that is unencrypted and located on the second layer of the OSI model of the packet. And we actually extract the packet length, the packet size, and the packet arrival time. And we actually create time series from these two features. And every time for the rest of the talk that I will refer to the time series extracted by this process, I will call them the intercepted bitrate signal. And you will know that when I actually discuss about the intercepted bitrate signal, I refer to this process, the two stages process that extracts the time series from the packets. Okay, so the first stage of is classify suspicious radio transmission as first-person view channel that belongs to a drone. And the key observation in here is that a drone is a flying camera. So by combining algorithms for moving device detection and for camera detection, you can actually determine that a suspicious Wi-Fi transmission is a first-person view channel. So one interesting thing that we found during this research is that when you take a drone and you analyze its intercepted bitrate signal, the magnitude, the most dominant magnitude in the spectrum domain is actually correlative to the frame per second rate. You can see in the left side a spectrogram of that was extracted from an experiment that we conduct, which we actually change the frame per second rate every 2 minutes from 24 FPS to 25 FPS to 30 FPS. And you can see how the spectrum actually out-affected the spectrum. So in order to detect a camera, what we need to do is to analyze the intercepted bitrate signal in the frequency domain, find the frequency with the maximum magnitude, and compare the frequency with the maximum magnitude to known frame per second rate of drones. And the list is, you can see it in the slide. However, just by doing the first stage, you will actually classify Wi-Fi video cameras as drones. So in order to exclude Wi-Fi video camera, we actually try to combine another algorithm, which is used to detect moving objects. Now, this area is investigated in research for many years. And one way to do it is just by analyzing the received signal stratification measurements for a given device. And when I say device, I mean a MAC over time. And RSSI is also something that can be extracted from, it's unencrypted and can be extracted from the same layer that you extract the packet arrival time, for example, or the packet length. And you can determine that a device is on the move according to the change of its measurement over time. You can see it for the case of a drone, for example. Okay, so by combining both algorithms to one algorithm together, we can determine that whether a suspicious radio transmission is a first-person view channel in 4 seconds with accuracy of almost 100% and very low false positive rate. Now let's talk about the second stage, which we try to detect whether the first-person view channel that we just classified is being used to spy after a victim. It means that the first-person view of the drone is video streaming a victim. And in order to understand how our method, I want to discuss about the video compression stage. The video compression stage is actually the stage before the encryption and the modulation of the data. And the standards are H.263, H.264, and H.265. These type of standards are being used in real-time video streaming, and they are used in all of the drones that we that we tested in this research. And one thing that you need to know about this standard is that it is called the motion compensation algorithm, and it works as follows. Instead of sending an entire frame, a frame is described as delta, as changes from another frame. And this information is sent in a GOP structure, a group of picture structure. Now, there are self-contained frames, which we call the I-frames. However, the vast majority of the frames is delta frames, which are B frames. And B frames that contain a description on how to extract the frame by using another frame. It can be, for example, an I frame or a P frame. And again, the data is sent in a group of picture structure. Now, the result of using this type of video compression algorithm is that there is a coupling between the physical changes in the recorded environment and the amount of data that is encoded and transmitted. And if there are a lot of changes between two consecutive frames, and this can be by, for example, the result of a movement between the two frames, large amount of data needs to be encoded and again transmitted to the operator. However, if there are minor changes between two consecutive frames, small amount of data needs to be encoded and again transmitted to the operator. So with that in mind, we placed a Wi-Fi FPV drone in front of an LED board. And we used the LED board as a 3 Hz flicker. We connected it to Arduino and we used it as 3 Hz flicker. And while operating the flicker, we intercepted the bitrate signal and created it. And you can see the picture below. And we analyzed it in the time domain, and we found very interesting phenomena. Every time that the flicker changed from on to off and vice versa, there's a burst appears in the time domain. Now you can see in here that since a 3 Hz flicker creates 6 changes between on to off and off to on, each and every time that a change appeared in the time, a burst appeared in the time domain, which correlative to the changes that were done in the physical environment. And the key observation in here is that a 3 Hz flickering LED created 6 bursts in the intercepted bitrate signal. So how you can leverage this understanding in order to detect whether a specific point of interest is being video streamed by a drone? All you need to do is to launch a flicker with a frequency f and test the change of magnitude of frequency 2f, 2 times the frequency of the intercepted bitrate signal in the frequency domain. You can see it in here to the left that each and every frequency can be watermarked by using this approach, and you can see how the magnitude is changed according to how dominant it become by triggering the flicker. You can actually see in the spectrogram where exactly a flicker was operated and in which frequency. So we can understand whether a drone is video streaming a point of interest by operating a flicker next to the point of interest and testing the influence of the flicker on the spectrum of the intercepted bitrate signal. And this can be done even if the transmission and the traffic is encrypted, because we are using unencrypted metadata. Okay, so let me show you the videos from 2 experiments that we did. The first experiment was in order to detect a spying drone when the victim is static and located inside the house. And the second experiment that we did was in order to detect spying a drone when the victim is actually on the move, when he is driving his car. Now, the first movie shows a smart film that attached to the window of the living room, and you can see that we are using the smart film as flicker. This is the first flickering episode. And there's a second flickering episode. That you can see now. And in this case, the victim is actually driving in its car, and there's a siren that is about to be operated. You can see it in here. Okay, so let's examine the results, and you can see that when the siren was turned on, you can see how the magnitude is actually become dominant around the watermark frequency. And you can see how the two flickering episodes in the first experiment that we did are actually dominant when you are observing the specific frequency. Okay, so we actually tested how good is our system in terms of false positive rate, what is the rate of the false alarms, and we found that we are able to detect a spying drone in 2 to 3 seconds with very good accuracy and very low false positive rate, as you can see in the graphs below. So as I mentioned, we can detect spying drone in 2 to 3 seconds with high accuracy and low. Okay, now the first stage is actually we were able to classify a suspicious radio transmission as FPV channel, and we know that this radio transmission is used to spy after a victim. And now we want to locate the spying drone in space using the things that we actually have. And the way that we do it is as follows. First, we place the drone in front of the LED board, and we changed the angle between the LED board and the drone, and we found that the magnitude around the watermark frequency changes as a function of the angle. You can see it in here. So we created a function that predicts the angle between a drone and 2 flickers, where each flicker operates at a different frequency. This is to the right, you can see the function, and this is based on the ratio of the magnitudes of the 2 watermark frequencies. And we computed one function to predict the horizontal angle and another function to compute the vertical angle. And by using somehow the same approach, we created a function to predict the distance, the radius between a flicker and a drone based on the magnitude of the watermark frequency. So in order to locate a spying drone in space, so basically, we apply the following stages. Given an intercepted bitrate signal, we calculate the following theta, phi, and radius. And theta and phi we compute them using the function to detect the angle, and the radius is computed using the function to detect the distance. And we predict the location of the spying drone from using the spherical coordinate known formulas. You can see them in here. And we wanted to test how good our prediction is. So we conducted another experiment. We took the LED board and placed it on the balcony of our organization. And we fly the drone to fairly different location in order to conduct spying against the balcony. And we tried to measure how accurate is our model in terms of locating the drone. And we found that we can estimate the location of a spying drone with an error of up to 3.5 meters for each axis again in 2 seconds using 4 strips of LED without using any expensive radar, without using any video camera, without using LiDAR, without using microphone array, only just by using a laptop and 4 LED strips. Okay. The last thing that I want us to discuss is how this entire method can be applied in an invisible manner. So the pilot of the drone won't suspect that someone is trying to detect that the drone is used for spying. And in order to apply the flicker invisibly, 3 requirements must be satisfied. The first one is that it should be undetectable by direct observation by the drone's operator. It means that if the drone's operator is located nearby and looks on the flicker, he won't recognize it directly. It should be undetectable by indirect observation via the drone's controller. It means that if the pilot of the drone will try to look on the drone's controller, he or she won't recognize that a flicker is being used. And it should also watermark the FPV channel in order for us to understand that the drone is being used for spying. And the way that we did it is by flickering between two similar hues. And we actually took two hues of the same color and tried and flickered between them. And this is undetectable by a direct observation because this technique exploits the inability of the human eye to distinguish between two almost similar hues. It is also, as a result, undetectable by indirect observation via the controller, and it watermarks the FPV channel, as I'm about to show you in the next slide. You can see that in the picture to the right, that these are actually the pictures from similar hues that we change the chroma component of the color, and you can see that for the naked eye it looks similar, and the use of this smart bulb looks similar, and you won't probably distinguish that this is another type of color. Now we actually conduct an experiment in order to understand whether this technique can be used to watermark the FPV stream at the intercepted bitrate signal, and you can see in here that unsurprisingly, as you increase the difference between the hues, the magnitude actually basically increased, and all of these are, as you can see in here, are indetectable to the human eye. You won't recognize that there's a flicker if it will operate near you. Okay, so about to conclude this talk, and there are three takeaways that I want you to think of. And the first one is that spying drones are turning into a real concern. And the threat of spying drones requires dedicated solutions to protect society. However, such solutions currently do not exist. And finally, the answer to the question of whether a country or a city should allow a company to use a drone to deliver its packages need to take other aspects beyond the business aspects into account. And for example, the ability to protect the privacy of the society should also be taken into consideration before allowing a drone to fly in populated areas. Okay, so first of all, again, I want to thank you for attending my talk. This research is based on a paper that we wrote and was accepted to IEEE Security and Privacy Symposium 2019. You can read more about this research at my website. The link is over here. And a recent paper of ours about security and privacy in the age of commercial drones was just accepted and will appear in IEEE Security and Privacy Symposium 2021. So you can find some other interesting related topics to drones, like about and discussions about privacy and mitigations and countermeasures and some other things, some other interesting things. Thank you once again.